In 1900, math predicted the end of the universe. It was known as the ultraviolet catastrophe. Classical physics, the same perfect math that mapped the orbits of the planets, stated something impossible. It dictated that if you heated a simple oven, the continuous electromagnetic waves inside would generate an infinite amount of high frequency ultraviolet radiation. Simply turning on a stove should have incinerated reality in a blinding flash. But it didn't. To save physics from theoretically destroying itself, a physicist named Max Planck published this paper. He realized that the continuous classical equations were fatally flawed and declared Wien's law invalid. He had to look at energy entirely differently. In a desperate mathematical attempt to fix the curve, Planck was forced to commit scientific heresy, and in doing so, he accidentally shattered classical physics forever. To calculate the energy of these discrete packets, Planck turned to probability. He imagined a system of resonators sharing distinct units of energy. By counting the number of ways to distribute these elements, he derived a brand new formula. Planck's genius was linking the size of this energy element directly to the wave's frequency. At high frequencies, the cost of a single energy coin becomes so massive that the oven cannot fund even one. The ultraviolet catastrophe is aborted. Planck calculated this new constant, h, yet he thought this quantum was just a statistical trick. Physics remained comfortable with the idea that light itself was a continuous wave propagating through space. 4 years later, Albert Einstein pointed out a fatal contradiction between discrete matter and continuous waves. He took Planck's mathematical trick literally. Einstein looked at a century of flawless wave theory and shattered it. Light itself, he declared, was a hail of bullets. Einstein proposed that a light ray consists of finite energy quanta that move without dividing, behaving like independent bullets. He proved this by mathematically solving the photoelectric effect, where light knocks electrons out of solid metals. His equation showed that a single light quantum delivers its entire energy to a single electron. To escape, it must perform work, P, the metal's toll booth. Dim red bullets fail, but a single blue bullet has the concentrated energy to smash right through. Einstein proved light was a particle, but fixing light broke matter. In 1913, Rutherford discovered the atomic nucleus. Physicists pictured atoms as in the solar systems with electrons orbiting a positive center, but applying classical physics revealed a fatal flaw. An accelerating charge must radiate continuous energy. As the electron bleeds its energy, the math is brutal. Its orbit aggressively shrinks. It must violently death spiral into the nucleus. Under classical physics, every atom in the universe should instantly collapse. To save the atom, Bohr did the unthinkable, intentionally breaking classical physics. In his 1913 paper, Bohr declared classical laws inadequate at the atomic scale. He postulated stationary states, specific orbits where the electron moves without radiating energy. But which orbits are allowed? Bohr locked the atom to a strict mathematical grade. In a stationary state, the electron's angular momentum cannot be random. It's strictly quantized. It must be an exact whole number multiple of Planck's constant divided by 2 pi. This single equation completely rebuilt the solar system of the atom. It replaced continuous empty space with rigid invisible train tracks. The electron can only exist on a track. If it tries to slowly degrade or drift into the empty space in between, the mathematics of the universe violently forbids it. The electron leaks. Instantly, a single photon carrying the exact energy gap. Bohr's tracks matched hydrogen spectrum perfectly, but nobody could explain why the tracks existed at all. Bohr's tracks were completely arbitrary. Why these specific paths? In 1924, Lewis de Broglie found the stunning answer. Since Einstein proved light waves act as particles, de Broglie proposed the radical reverse. Solid electrons must act like waves. He proved that any moving body has an internal frequency and is accompanied by a phase wave. This wasn't abstract philosophy. It unlocked the atom. When circling the nucleus, the phase wave must travel along the orbit. But on the precise tracks where the wave bites its own tail, the harmony persists. Bohr's impossible tracks were just the natural harmonic resonances of matter waves. The quantum enigma was solved, but exposing this wave miniature ignited the most bitter mathematical war in scientific history. His matter waves were elegant but they failed catastrophically for anything more complex than hydrogen. In 1925, Werner Heisenberg realized that the entire visualizable model of atomic orbits was a lie. The old rules tried to map quantities that are unobservable in principle. No one had ever seen an electron's exact path, so Heisenberg demanded a ruthless purge. We must discard all hope of observing these hidden quantities. He founded a new mechanics based exclusively on things we can actually measure, like the frequencies of emitted light. Heisenberg replaced continuous classical space with discrete systems of numerical quantities, creating a true theory of discontinuum. He built a bizarre mathematical realm using grids called matrices where multiplying position by momentum yielded a physically different result than multiplying momentum by position. Order mattered. Reality was now an abstract spreadsheet of observable transitions. But across the battle line, Schrödinger despised this abstract approach. He wrote that he was discouraged, if not repelled, by Heisenberg's difficult algebra and his complete want of prosperity or visual intuition. Schrödinger hated the stifling of intuition. In pure retaliation, he formulated wave mechanics, forcefully returning the quantum world to a continuous vibrating fluid. In his 1926 paper, Quantization as a Problem of Proper Values, Schrödinger banished Bohr's arbitrary quantum jumps. He formulated a continuous wave equation where discrete energy levels emerged completely naturally, behaving exactly like the geometric proper values of a vibrating guitar string. Physics was now violently torn. Heisenberg's discrete, unvisualizable matrices clashed against Schrödinger's continuous wave fields. As Schrödinger wrote, they departed from classical mechanics in diametrically opposed directions, yet impossibly, both theories perfectly predicted the exact same experimental results. How could two diametrically opposite theories both be right? Schrödinger mathematically dissected Heisenberg's matrices and discovered an astonishing secret. Heisenberg's discrete transition numbers were not just abstract algebra, they could be derived directly from the continuous wave fluid. If you take Schrödinger's continuous wave functions and integrate them across all of the space, they perfectly calculate Heisenberg's exact matrix elements. Schrödinger published a flawless mathematical proof demonstrating the absolute formal identity of the two theories. The discrete matrix and the continuous wave were mathematically the exact same thing. The quantum war was finally resolved. The mathematical war was over. Heisenberg's discrete matrices and Schrödinger's continuous waves were proven to be identical, but a profound physical mystery remained. If the universe is fundamentally made of continuous, mirrored out wave functions, why does the everyday macroscopic world look like solid, distinct particles moving on precise classical paths? How do quantum waves become solid matter? To answer this, Schrödinger built a continuous mathematical bridge from micromechanics back to classical macromechanics. He started with a fundamental wave equation for a simple quantum oscillator. A single quantum state is a standing wave that stretches infinitely across space. But what happens if you mathematically combine or superimpose an enormous number of these higher order proper vibrations all at once? Through mathematical superposition, the waves undergo extreme destructive interference, violently cancelling each other out to a dead flat zero almost everywhere. But in one highly localized region, their phases perfectly align. They constructively combine to form a dense, compact wave group, a tall, narrow hump of pure wave energy. He proved that this tight packet of waves always remains compact. It does not smear out or dissipate over time. Instead, the entire wave group oscillates back and forth following the exact same mathematical equations as a classical particle. The solid microscopic matter we observe in our daily lives isn't a solid point at all. It's nothing more than a tightly packed bundle of quantum waves riding in perfect mathematical harmony. The mathematical bridge was complete, but a profound existential crisis remained. What actually is this vibrating quantum wave? If the solid electron is just an illusion created by a bundle of waves, what physical substance is waving? In the final paper of his series, Schrödinger attempted to give the abstract wave function psi attainable physical reality. He introduced a radical heuristic hypothesis. The wave was not just a mathematical trick. By multiplying the complex wave function by its conjugate, he obtained a real positive value. Schrödinger declared that this resulting function represented the actual continuous space density of electricity. The electron was not a tiny solid marble flying through a microscopic void. Instead, the electron's charge was smeared out. Schrödinger wrote that the wave mechanical structure of the atom is a continuous superposition of all the point mechanical configurations kinematically possible. The electrical charge was distributed throughout space like a fluid, acting as a weight function, highly centralized in certain continuous geometric nodes and fading away to absolute zero in others. He proved that if you mathematically integrate this weight function over the entire configuration space, it remains constantly normalized. The total electrical charge is perfectly conserved, but the point particle is gone. This was the ultimate staggering realization of the quantum break. Matter at its most fundamental level had completely dissolved from solid geometry into vibrating continuous field of electrical probability. Bohr's 1913 atomic model had successfully saved matter from collapse, but it suffered from a glaring blind spot. The quantum leap was a complete theoretical black box. Bohr simply postulated that an electron teleported between tracks and miraculously spat out a photon, but no one knew how this emission physically occurred. Schrödinger realized that his new continuous wave mechanics could finally reveal the mechanical anatomy of a quantum jump. Schrödinger modeled the transition as a continuous process where two proper vibrations exist simultaneously. If an atom is transitioning from a higher energy state to a lower one, both wave functions represented by the distinct geometric harmonious patterns are mathematically superimposed. Because these two continuous waves vibrate at entirely different frequencies, their overlapping phases cause extreme physical interference. Just like two out-of-tune guitar strings played together create a rhythmic pulsing sound, the superimposed quantum waves create a throbbing electrical beat inside the atom. The smeared out electrical charge literally washes back and forth across space. Schrödinger proved that the physical frequency of this beat is exactly equal to the energy difference of the two states divided by Planck's constant. Bohr's magic teleportation was an illusion. The atom acts exactly like a microscopic radio antenna. The emission frequencies are simply the deep difference tones of the vibrating matter waves. The oscillating electrical dipole moment finally allowed physicists to calculate the exact intensity and brightness of the spectral lines. But just as wave mechanics seemed utterly flawless, Schrödinger was about to collide with a terrifying new mathematical dimension, Einstein's theory of relativity. Schrödinger's continuous wave mechanics perfectly predicted the hydrogen atom, but only at low velocities. He knew he had to merge his vibrating fields with Einstein's theory of relativity. In his 1927 paper, Schrödinger extended his equations into a four-dimension space-time continuum by introducing an imaginary fourth coordinate, time multiplied by the speed of light. He transformed his wave equation into a fully relativistic master equation. By applying Hamilton's principle to this new 4D space, Schrödinger successfully derived the complete energy momentum theorem for material waves. The vibrating waves now perfectly conserved energy, momentum, and electrical current, beautifully blending classical electrodynamics with quantum mechanics. It seemed to be the ultimate, flawless theory of reality. The wave had conquered the universe. Schrödinger's continuous wave mechanics perfectly predicted the hydrogen atom, but only at low velocities. He knew he had to merge his vibrating fields with Einstein's theory of relativity. In his 1927 paper, Schrödinger extended his equations into a four-dimensional space-time continuum. By introducing an imaginary fourth coordinate, time multiplied by the speed of light, he transformed his wave equation into a fully relativistic master equation. Schrödinger realized something profound was missing. His 4D field scalar could not account for a radical new concept, the spinning electron. Wave mechanics could brilliantly smear out an electron's charge into a continuous fluid. But how do you mathematically spin a continuous fluid without tearing it apart? The grand unification of relativity and quantum waves had just hit a terrifying, unsurmountable brick wall. Defeated by the relativistic spin, Schrödinger retreated to his many-dimensional non-relativistic space to solve one final, crucial mystery. How do two quantum systems actually exchange energy? He desperately wanted to prove that the mysterious quantum jumps were not sudden, random teleportations, but were instead nothing more than classical continuous wave resonance. By combining the two systems and adding a small coupling term, R, the mathematics seemed to give Schrödinger exactly what he wanted. The equations showed the amplitudes of the two waves exchanging energy perfectly and smoothing over time. Without any discrete quantum postulates, the math produced a simple resonance phenomenon, exactly like two sympathetic macroscopic pendulums transferring momentum back and forth. But this beautiful, continuous, deterministic picture contained a fatal flaw. It could not explain thermodynamic equilibrium. To make the math match the real world behavior of gases and the heat baths, Schrödinger was forced to do the very thing he hated. He had to surrender the physical reality of the waves and introduce a purely statistical hypothesis. The squares of the wave amplitudes could no longer represent physical electrical density. According to Max Born's new theory, they were merely probabilities. The relative frequency of finding a system in a specific discrete state. Schrödinger admitted in his final paper that he was deeply adverse to his conception. The solid, predictable clockwork universe of classical mechanics was officially dead, replaced entirely by a permanent, irreversible field of quantum probability. Even as probability invaded his theory, Schrödinger refused to give up the continuous wave, but he faced a massive hurdle, the Compton effect. Experiments had shown that when light hits an electron, it scatters exactly like two solid billiard balls colliding, seemingly proving Einstein's light bullets once and for all. But Schrödinger was determined to explain this violent collision of purely wave kinematic ideas without ever invoking a single particle. Instead of solid marble, Schrödinger modeled the electron's initial and final states as two separate waves crossing through space. When you mathematically superimpose these two waves, they interfere. The difference of their propagation vectors creates a beautiful stationary interference pattern, a thick glowing wave of electrical density. The solid electron is replaced by a temporary vibrating crystal lattice. Now, the incident light wave enters the space. It doesn't strike a localized particle. Instead, it strikes the thick electrical density grid. Because the grid is periodic, the light wave reflects off the interference fringes exactly the way X-rays reflects off the geometric layers of a solid crystal. The collision is entirely governed by Bragg's classical law of reflection. The sudden change in the light's direction and frequency wasn't a particle collision at all. Schrödinger proved there is a complete reciprocity between the matter waves and the light waves. What the world thought was two microscopic billiard balls violently bouncing off each other was mathematically nothing more than the Bragg's reflection of a light wave of a temporary mirror made of matter waves. The illusion of the particle was flawlessly recreated by the wave. The continuous wave had recreated the illusion of the particle, but to survive, a theory must make flawless real-world predictions. The ultimate test was the Stark effect, the mysterious splitting of atomic spectral lines when placed in a massive electrical field. Heisenberg's discrete matrices promised the way to calculate the exact intensities of these split lines, a feat Bohr's whole tracks could never achieve. Schrödinger set out to prove his waves could do it better. He injected a perturbing electric field term directly into his wave equation. The external field destroys the perfect symmetry of the atom, the single overlapping wave harmonics, a state of degeneracy, violently shattered into multiple distinct vibrations. The single beat frequency of this atom is mathematically split into a chorus of different tones. By applying classical perturbation theory, Schrödinger proved that the proper values of the energy levels naturally split apart. To find the brightness of these new lines, he didn't use abstract matrices. He simply integrated the physical geometry of the distorted wave clouds, calculating the exact amplitude of the electrical dipole moments. The spatial continuous fluid directly dictated the intensity of the light. The results were an undeniable triumph. When Schrödinger calculated the intensities for the Bomber lines, his theoretical wave math perfectly matched Johann Stark's actual experimental measurements. The continuous wave had conquered the atom, but this ultimate victory came at a devastating philosophical cost. To accept his flawless math, physics had to permanently abandon the classical clockwork universe, surrendering reality entirely to absolute primary probability. With reality surrendered to probability, the new quantum mechanics was poised to destroy another fundamental assumption of classical physics, the existence of absolute zero. From a swinging pendulum, it comes to a complete dead stop at the bottom of its arc. Classical mechanics dictated that in its lowest state, the energy of an oscillator is exactly zero. But when Werner Heisenberg applied his radical new matrix mechanics to the simple harmonic oscillator, the math refused to yield zero. By forcing the observable transition amplitudes into his discrete kinematic rules, Heisenberg derived a new energy formula. The energy was equal to the quantum number 10 plus an inescapable, seemingly bizarre fraction, 1/2. Once later, Schrödinger tackled the exact same oscillator using his continuous wave mechanics. He solved the differential equation using Hermite polynomials. When he extracted the boundary proper values, the exact same mathematical anomaly appeared. Half integral multiples of the quantum of energy, despite their bitter feud and diametrically opposed starting points, both physicists independently proved that the classical formula was fundamentally wrong. This half-integer term revealed a terrifying physical truth. If you drop a quantum number into its absolute lowest possible state, setting the quantum number and equal to zero, the energy does not vanish. It equals 1/2 h times nu. The pendulum at the bottom of the well can never completely stop. This was the definitive mathematical proof of the zero-point energy. The quantum break had revealed that the vacuum of space is never truly empty. It is forever boiling with inescapable residual vibration. To finalize this new reality, de Broglie had to explain how a smeared out wave could trick us into seeing a solid moving particle. He mathematically proved that the particle is actually a dense packet of many overlapping waves. Because of relativity, the internal ripples, the physical waves, travel faster than the speed of light. But because they slightly differ in frequency, they interfere with each other. The resulting envelope or group velocity moves strictly slower than light. The velocity of this moving wave group is the exact energy velocity of the electron. When we zoom out to the macroscopic scale of our everyday lives, the dimensions of this wave packet become so infinitely small that it completely loses its undulatory character. To our crude human eyes, the dense wave packet looks and acts exactly as a solid point of matter following a perfect classical trajectory. But the solid particle is a lie. As Schrödinger concluded, the wave function psi times its complex conjugate acts merely as a weight function in configuration space. The electron is an overlapping superposition of all kinematic possible configurations at once. We do not live in a clockwise universe of hard marbles and unpredictable paths. At the absolute bedrock of nature, matter is nothing but a localized concentration of pure vibrating probability. In just 25 years, 6 revolutionary papers completely dismantled centuries of flawless classical physics, from Planck's desperate mathematical heresy to prevent the destruction of the universe to the bitter, spiteful clash between Heisenberg's matrices and Schrödinger's continuous waves. They didn't just reference reality, they broke it, exposing a bizarre, quantized universe that we are still struggling to comprehend today. While the quantum revolution unified the single electron atom, Bohr had actually attempted to build the entire universe from his quantized tracks. He didn't just stop at hydrogen, he expanded his math to construct molecules, arranging multiple electrons at equal angular intervals in a single rotating ring. To balance the repulsive forces between the electrons and the attractive pull of the nucleus, Bohr derived a new centrifugal equilibrium, but to lock this molecular ring into reality, he instituted a universal law. In the permanent state of any molecular system, the angular momentum of every single electron around the center of its orbit must be exactly equal to the Planck's constant divided by 2 pi. But this molecular model harbored a fatal flaw. While the ring was mathematically stable if you pushed an electron up or down, classical mechanics proved that any slight displacement of an electron within the plane of the ring would cause the entire atomic structure to instantly violently shatter. Bohr's visual geometry was failing for complex systems. To fix it, physics had to abandon the visual picture of rings entirely and trust Werner Heisenberg's abstract spreadsheets of transitions. But Heisenberg's new matrix mechanics had to prove it could survive where classical models failed. It had to face the ultimate mathematical stress test, the unharmonic oscillator. In the real world, the atomic forces holding systems together are not perfect, symmetrical springs. If an electron is pushed too far, the restoring force becomes skewed and asymmetrical. In classical mechanics, this is called an unharmonic oscillator, governed by adding a nonlinear perturbation term lambda x squared to the equation of motion. Could Heisenberg's discrete, unvisualizable matrices handle this nonlinear chaos? Yes. By forcing the classical power series into his new quantum theoretical kinematics, Heisenberg derived a brutal, infinitely scaling set of recursive matrix equations. To find a single transition amplitude, the matrix had to recursively call upon the amplitudes of all the neighboring quantum states. Through excruciating algebraic manipulation, discarding all terms of order lambda squared, he isolated the diagonal elements of the energy matrix. He proved that the quantum energy levels of the asymmetrical well shift perfectly, and they do so without ever needing a single classical orbit. Heisenberg's matrices has passed the test, but Schrödinger was ready to strike back. He wanted to prove that his continuous wave mechanics could handle perturbations even more elegantly. He set his sights on the Stark effect, the violent shattering of atomic light when an atom is crushed inside a massive external electric field. When you apply a high voltage electric current to an atom, the spherical symmetry is destroyed. To mathematically survive this, Schrödinger abandoned standard geometry and rewrote his wave equation using space parabolic coordinates, a complex web of intersecting confocal paraboloids of revolution. He injected the perturbing electric field term minus EFC directly into his continuous wave equation. Immediately, the single degenerate frequency of the atom fractured. The mathematical proper values split apart, mirroring the exact splitting of the energy levels observed in the laboratory. But Schrödinger went further. Heisenberg claimed matrices were required to calculate the brightness or intensity of these split spectral lines. Schrödinger proved you only needed to take a spatial integral of the continuous electrical density. As you integrate the volume of the vibrating wave clouds, it directly calculates the exact amplitudes of the light. When he compared his wave calculated intensities against Johann Stark's experimental data for the Bomber lines, the numbers smashed flawlessly. Wave mechanics seemed invincible, but as Schrödinger pushed his math to its absolute extreme, attempting to merge the wave with Einstein's theory of relativity, he hit an impenetrable mathematical wall. To make wave mechanics relativistic, Schrödinger upgraded his wave equation to a four-dimensional spacetime continuum using the electromagnetic potentials of the external field. But when he solved this relativistic master equation for the hydrogen atom, the theoretical fine structure diagram turned out mathematically deformed. The continuous wave equation incorrectly forced the appearance of half-integral azimuthal quantum numbers, directly contradicting experimental measurements of hydrogen. Schrödinger realized a fundamental physical property was missing from his continuous fluid, the magnetic spin. Other physicists had proposed that the electron was a tiny, rotating point charge, a spinning marble, but wave mechanics had dissolved the marble into a smeared out cloud of electrical probability. How do you mathematically assign an intrinsic magnetic spin to a continuous, infinite probability wave without tearing the geometry of the space time apart? Schrödinger couldn't do it. The grand unification of relativity and the quantum wave was left broken.